For decades, biochemical dogma taught that exposing a folded protein to a chemical denaturant like urea collapses it into a random coil. The classical assumption was that breaking a protein's hydrogen bonds reduces the polypeptide to a state of maximum entropy and structural chaos. Spectroscopic data contradicts this. In the so-called unfolded state, a highly specific structural conformation dominates, the Polyproline II, or PPII helix. Remarkably, this occurs even in proteins that do not contain a single proline residue. This presents a structural paradox. The classical structures we know, alpha helices and beta sheets, are locked in place by periodic internal hydrogen bonds. The PPI2 helix lacks these internal stabilizing bonds entirely. The PPI2 geometry has been a known quantity since the 1950s, when biophysicist G.N. Ramachandran first published the triple helix structure of collagen. Yet the central conflict remains. Urea is an agent defined by its ability to tear apart hydrogen-bonded networks. Why does a molecule designed to disrupt structure actively promote and stabilize the PPI2 helix? To find the answer, we must look past the classical mechanics of steric clashes and ball and stick models. The solution requires an analysis of quantum stereoelectronics. The unfolded state is a highly governed structural regime, driven by molecular forces that operate below the threshold of classical microscopy. The dominant force in this regime is the N to pi star interaction. This stereoelectronic mechanism provides 1 to 3 kilocalories per mole of stabilization energy for every residue in the polypeptide chain. Here are the exact orbital mechanics. Stabilization relies on through-space electron delocalization. A donor oxygen's lone pair, the N orbital, overlaps with the adjacent carbonyl's empty pi star orbital. This aligns the interaction angle at roughly 107 degrees, pulling the oxygen and carbon atoms closer together. In a folded protein, a carbonyl oxygen must allocate its lone pairs. It can participate in a traditional hydrogen bond to secure an alpha helix, or it can engage in this stereoelectronic N to pi star interaction with its immediate neighbor. Because the Polyproline II helix lacks competing internal hydrogen bonds, its carbonyl groups are free to maximize these N to pi star overlaps along the backbone. The N to pi star interaction is the stabilizer of the protein backbone, acting as the primary focal point for solvent-induced structural changes. To isolate how solvents affect this scaffolding, we strip away the bulk of side chains, leaving this twisted parallel offset formaldehyde dimer. Simulated in implicit water, it represents an energy minimum. In a vacuum, it falls apart. The local environment is required to maintain stability. We measure the strength of this interaction using two exact metrics, the intercarbonyl distance, labeled D, and the extent to which the acceptor carbonyl physically deforms out of a flat plane, a measurement called pyramidalization, labeled delta. If introducing a solvent alters the geometry of this minimal model, it proves the solvent acts through direct electronic modulation of the carbonyls, not through steric interference. An implicit solvent acts as a uniform dielectric background. Explicit solvation introduces specific molecules that form direct hydrogen bonds with the carbonyl groups. This scatter plot maps the interaction energy against the intercarbonyl distance. The correlation is absolute. As the physical distance between the oxygen and carbon atoms decreases, the interaction energy becomes significantly more stable. Adding solvent does not uniformly compress the molecule. There is a strict functional asymmetry. Solvating the donor carbonyl weakens the interaction. But solvating the acceptor carbonyl strengthens it. This is driven by an electrophilicity shift. When a solvent hydrogen bonds to the acceptor oxygen, it withdraws electron density. This lowers the energy of the adjacent pi star orbital, making it a more effective sink for the donor's electrons. Comparing models with one solvent molecule versus two reveals a drop in distance and increased pyramidalization. Maximum stabilization is achieved when two solvent molecules are anchored on the acceptor carbonyl. This configuration simulates a fully hydrated state, yielding the strongest possible electron delocalization. Protic solvents like water actively drive shorter, tighter N to pi star interactions by electronically preparing the acceptor carbonyl for nucleophilic attack. We apply this rule of acceptor solvation to chemical denaturants like urea, thiourea, or guanidium. The urea complex reveals a distinct advantage. Urea forms bidentate hydrogen bonds, simultaneously engaging both oxygen lone pairs on the acceptor carbonyl. This grip creates the tightest N to pi star distances recorded, 2.741 angstroms, explaining why urea is such a potent stabilizer of the PPII helix. Scaling to full peptide models confirms this dictates secondary structure. Urea on the acceptor carbonyl shifts the energy, favoring PPII over the beta state. The beta state dismantles because solvating the alanine carbonyl weakens the internal C5 hydrogen bond, allowing the backbone to extend. Urea denatures proteins by outcompeting interresidue hydrogen bonds, but it stabilizes the PPII helix by intensifying the backbone's internal electronic delocalization. The classical Ramachandran plot defined protein folding through steric boundaries, atoms physically colliding. The modern view maps the electronic driving forces pulling those atoms together. Solvents and denaturants are active structural ligands that dictate the geometry of the polypeptide chain in its denatured state. Quantifying these interactions provides the variables required to understand intrinsically disordered proteins and the energetic cost of folding the first turn of an alpha helix. By tracking the N to pi star interaction, we see that the unfolded polypeptide follows a strict quantum logic, where structural preferences are determined by the local stereoelectronic environment.